Hi everyone, welcome to my talk about new suse-kabi tools which provide fast and detailed kernel ABI comparison. This is a small project that I've been working on. The talk consists of 4 parts. The first one offers a brief introduction to KEBI and what stability guarantees are provided by SUSE. The second part shows the current workflow and tools used by the SUSE kernel build to detect KEBI changes, and it then discusses their issues and limitations and outlines some options how to improve this operation. The next part shows newly implemented workflow and its tools, and it then demonstrates how they provide an improved analysis of KPI changes. And finally, some summary. The session should provide a good overview of the new SUSE KPI tools, how they fit into the current tooling, and how they help in understanding KPI changes. So let's start with a quick introduction to what is meant by ABI and KEBI. Most people here should be familiar with these terms, but it's good to make sure that everyone understands what I will be talking about. ABI stands for Application Binary Interface, and it's an interface between two binary program components. The ABI defines how functions and data structures are accessed at low level in machine code. It should not be confused with API, which means Application Programming Interface. The API defines the access at a higher level in source code. The Linux term KEBI then stands for Kernel ABI, and it's an agreed upon interface between the Linux kernel and its modules. An ABI comprises a set of exported functions and variables, function parameters and their return values, the layout of data structures, and calling conventions. Some properties, such as the last mentioned calling conventions, are guaranteed by the compiler by adhering to the respective architecture-specific ABI. These properties are somewhat implicit when discussing KEBI and not that much of interest. The first 3 items are more interesting for us because they are directly affected by developers making changes to the kernel source code. The upstream Linux project doesn't maintain a stable API nor ABI. In an ideal world where all modules were developed upstream, this would not be much of an issue. However, some parties wish to develop out-of-tree modules, and they also have limited resources, so they would like to build their module against one version of the kernel, but be able to use it with different kernel versions. And this presents 2 problems. The first one is that the module might not work correctly with a different kernel version. The upstream kernel helps with this, and it provides so-called mod versions, which is a per symbol safety mechanism to recognize and prevent loading of incompatible modules. And this then enables potentially for a module to be safely loaded on a different kernel than it was originally built against. The follow-up problem is if the kernel gets updated and some relevant symbol is changed, then one still needs to go and update and rebuild their module. Some Linux distributions, typically commercial ones, help with this, and they guarantee stable KEBI downstream for a certain series of kernel updates. Specifically in SLES, the guarantee is to keep KEBI stable for all kernel updates in a given service pack. This allows external parties to build their module against the first general available kernel in the given service pack, and for their users to be able to load it on any kernel from the same service pack. The overall implementation to keep KEBI stable depends on 2 parts. The upstream provides the mentioned functionality to check KEBI compatibility, and SUSE then has additional tooling to maintain KEBI stability. And my talk and the new tools are mostly about the latter, about KEBI stability and detecting KEBI changes. So that was context. Now let's have a look at the current implementation. The current workflow to check KEBI stability during the RPM build of suse-kernels consist of several steps, and this is a simplified overview. First, the downstream script mod versions, it unpacks the consolidated sim types reference from its KBI location, and it splits it into individual simref files. The kernel spec recipe then performs a regular kernel make, and during this operation, the upstream tool GenKsims is invoked for each source file, and for each file, it determines expanded type definitions of all exports within the file, reports any differences compared to the associated simref files, calculates simple CRCs from the expanded definitions, and writes the new type data into a simtypes file. The build also invokes another tool, modpost, which as part of its operation collects all calculated CRCs to the module simverse file. Following that, the mod version script is invoked again, and this time it merges all the new simtypes files into a consolidated file. This is useful for debugging the process or potentially as a new reference. And finally, another downstream script, KABI-PL, it compares all new symbol CRCs with another reference from the KABI location. This operation takes into account the suse-kabi severity rules, and the build is aborted on a mismatch. The entire operation works with two main file formats. The first simtypes format records information about all type definitions which were used in calculation of symbol CRCs. It is a simple key value format with some cross references. This example shows two functions, register module notifier and unregister module notifier, and both functions take a pointer to notifier blocks structure as their parameter. The data then contains the definition of the structure along with all other type that it recursively uses. The SUSE kernel build uses two variants of this format. The base upstream variant allows to describe the types in individual objects, and the SUSE-specific consolidated variant extends it and allows for the description of multiple objects, typically covering the entire kernel. The second simverse format records information about all exported symbols and the final CRCs. It also includes information in which module each symbol is defined, then the export type, and optionally also the symbol namespace. So this example shows the output when some symbols change. In this case, I've added a new field to the notifier block structure. The first part is produced by GenKsims, and you can see that the tool recognized that the KABI of the functions register module notifier and unregister module notifier is changed because of the changes in the notifier block structure. The second part is produced by the downstream script KABI-PL, and it reports the change symbol CRCs, and the build then gets aborted. And this is fairly good output, but it has some limitations. The first problem is that the information is somewhat scattered. So you receive a message about change symbol CRCs at the end of the build when it fails, but you need to know and search the log to actually understand why this happened. Another problem is that the information is limited and GenKsims doesn't actually tell you exactly what changed. And another problem is that GenKsims doesn't take into account suse-kabi severity rules, so you can get spurious warnings about some change symbols, even though such symbols should be ignored. This slide shows the overall workflow again. This time, each step taken to check KBI stability is annotated with time that it contributes to the total build time. Note that this doesn't include the time taken by spent by GenKsims to calculate symbol CRCs, because that is always necessary. even if actual KBI stability is not needed. The measurement was done with Li15SP6, its default variant, and on a machine that has 160 CPUs. The first mod versions unpack step takes 37 seconds. It splits the 30 megabyte consolidated file into 440 megabytes of individual syntypes files. Then the regular kernel make is performed from the KABI stability perspective. Only the comparison done by GenKSims contributes to measured time. And because make can run GenKSims in parallel, the contribution is minimal. Following that, the mod version spec step takes 17 seconds, and the final comparison done by KBI is trivial, and it takes less than 1 second. The total build time in this case was 787 seconds, with 54 seconds spent on KBI stability processing, and this constitutes 7% of the total build time. So as shown on the last two slides, the current tooling has some issues and limitations. The output is good, but not great. It is scattered, contains repeated information, and provides limited detail about what has exactly changed. Then GenKSims can produce spurious warnings because it doesn't take into account suse-kabi severity rules. The overall operation is also relatively slow. Checking KBI stability contributes a significant portion of the build time. And finally, another limitation not yet mentioned is that this workflow works only with GenKSims. So Upstream recently added a new tool called GenWorkKSims, which obtains symbol information by reading Word data instead of pre-processing source files. And this tool is needed to support mod versions for Rust. But unlike the current GenKSims, GenWorkKSims lacks any detailed comparison. So if we want to eventually support Rust in the SUSE kernel, another tool needs to provide this comparison functionality. I will mostly skip this slide because I don't have that much time. But basically, there are several tools used by other distributions which could be adopted by SUSE Linux to improve its operation. I evaluated them, but they didn't seem to me to be quite suitable for SUSE Linux. The main obstacle is that the full KABI scope of SUSE Linux covering the entire kernel, it makes the runtime of these tools too slow. And I really didn't want to increase the current build time, but there are other limitations as well. I instead eventually decided to write some new tools to replace and improve the current downstream script. So I started last year working on a new set of tools to replace the downstream script RPM mod versions and RPM KBI PL, as well as the comparison functionality provided by GenKSims. The tools have two design goals. The first one is to be reasonably fast, which in practice means that they should be written in a compiled language and they should utilize some level of parallelism for the most expensive operations. And the second goal is that they should provide somewhat more detailed KBI comparison compared to the current GenKSims output. The idea is to simply utilize the full information that is available in the syntypes data. The two new tools are KSimtypes and KSimverse. KSimtypes is a tool to work with syntypes files. It allows to consolidate and compare syntypes data, and the comparison doesn't require for the data to be unpacked first. The tool replaces the downstream script RPM mod versions and the functionality and the comparison functionality provided by GenKSims. KSimverse is a tool to work with Simverse files. It allows to compare Simverse data, and it takes into account suse-kabi severity rules. The tool replaces the KBI PL script. The overall operation changes a bit with suse-kabi tools. The most time-consuming unpack step is completely gone because we no longer rely on gen k-sims to do the detailed comparison, and the new k-sim type tool can directly work with consolidated data. Then we have, therefore we start with the regular kernel make, and during it, gen k-sims is invoked as usual, and it performs the usual operation to calculate symbol CRCs, but it no longer does any comparison. Following that, the mod version spec step is replaced by k-sim types consolidate. The operation mostly remains the same. It merges all the new sim types files into a consolidated file. Similarly, the KABI PL script is replaced by k-simverse compare. The operation also mostly remains the same. It compares all new symbol CRCs with their reference. New step, k-sim types compare, is added to compare the new consolidated sim types data to their reference. And this then provides detailed information about change types. A single report is now about KBI changes is now present in the kernel build log. First, the case-inverse tools provide information about change symbols and whether they were tolerated by the suse-kabi rules. This mostly remains the same as before. Then the k-sim types tool provides detailed information about change symbols. For each change type, it collects all exports affected by the change, and it also formats the original and new definition of the change type and shows their difference as a unified diff. This shows the overall workflow again, this time with the focus on runtime. So the first k-sim types consolidate operation takes 9 seconds on this machine. The command is able to read individual sim types files in parallel, which helps a bit. The kernel spec recipe simply passes the SMP RPM flags to the tool, which allows it to, in this case, to use up to 160 threads. However, this number of threads is quite overkill for this operation, as the problem doesn't scale particularly well, or if you want, my solution doesn't scale that well. For a reference, I've added on the right side of the slide how long it takes to run the command using only a single thread. The case-inverse compare command completes trivially in less than 1 second. And the final case-inverse, k-sim types compare command is conditional on the previous inverse comparison. So if no symbol changed or if all changes were tolerated by the suse-kabi severity rules, then the comparison is completely skipped. If a detailed report is necessary, then the tool can compare the entire KABI with its reference in about 7 seconds. And this scales reasonably well. Some improvements in speed are still possible. Nonetheless, in this specific test, the time spent on KABI stability processing is already reduced to 1% of the total build time, down from 7%. So suse-kabi-tools exist as a separate project from the kernel source repository, unlike the current scripts. The downstream kernel spec file then gains a build dependency on the new suse-kabi package. The tools are written in Rust. The implementation relies solely on the Rust standard library with no external dependencies. This is because I wanted to avoid a situation where adding some utility crate would pull in dozens of additional crates as dependencies, which would require additional maintenance. The project has 3,000 lines of code plus 2,000 lines of tests, so it's relatively small. Source code is hosted on GitHub under the SUSE organization, and the development package is present in the OpenSUSE build service. The tools should be hopefully feature complete. it helps that the scope what the tools intend to do is limited and I believe well understood. Some optimizations and polishing still need to be done, and I also anticipate feedback from users regarding the output format. So that's also expected to improve over time. More features could be added if other distributions find these tools interesting, such as support for stable list. And the project is expected to have low maintenance. Being written in pure Rust is one aspect that should help in this regard. Final summary. So suse-kabi-tools is a new set of KBI tools which replace and improve the previous downstream scripts. The main benefits of these tools is faster downstream build, improved output detailing KBI changes, and the ability for the SUSE kernel to use Gen-dwarf K-sims. As mentioned, the problem with Gen-dwarf K-sims is that it lacks any comparison functionality. Additionally, with suse-kabi-tools and Gen-dwarf K-sims, I believe that there shouldn't be a need for the SUSE kernel to use any additional, more complex dwarf tooling, which some other distributions use. The tools are expected to be deployed starting with SUSE Linux 16.0. This should hopefully happen soon if everything goes well. And there is also an option to backport these tools to SLE15 as all data formats remain the same. In particular, the format of the consolidated syntypes data, which actually happens to be shipped as part of the kernel development package. So this format remains the same. Yeah, that's everything. And we have 5 minutes for questions.
One of the prevalent current tools is that sometimes it does not detect that some changes are completely innocuous, and that should be ignored, so that we have to add some if def GCX. For example, two cases come to my mind. One is a patch adds new include, and you get all those became defined warnings, because there is a structure that used to be just a black box because before. Now we know what does it look like, which changes the GenKC output. So there is the identified as change of KABI, even if there is absolutely no change. Second case, for example, you add a new structure member into a whole, but it does change formally the KABI, but the binary interface did not actually change. It was kind of extended only. So do the new tools try to be kind of smarter in these cases?
Not really, because they rely on the output generated by GenK-sims, and there is no change to GenK-sims.
Thank you.
Yeah, I like that the new tool shows that, so what breaks, and that's great. My question is, when I want to have a check only for the partial compile, so only one file, is it still possible?
So this is something that I thought about it, but I wasn't sure if it's something that people use, but it can be definitely added. So it's not currently supported. So if you now try to compare a sim types output, which was produced only for a individual object file, and you compare it with the entire KBI reference, and you will get a huge amount of changes. So this is about adding some option to tell the tool that it should take only a portion of the reference file and consider it for the comparison. It can be added.
Mm-hmm. Well, currently we can still unpack the files beforehand and just compile one file, and then Jenkins Sims will complain if something broken.
Yeah, that should be also possible. but then you will get only this less detailed output from gen k-sims. So you probably would add support for what you mentioned directly to the k-sim types too. So you should be then able to use it, and it will provide this more detailed output.
Okay. And another question is, I think you are involved with upstream in dwarf the KBI things.
Mhm.
Yeah, and so will eventually will use that stuff in the future, or it's not our interest?
You mean if we plan to use gen dwarf k-sims?
Yeah, I only remember vaguely that the upstream has some development for the KBI stuff that using directly or dwarf or
Mhm.
what?
Yeah, so I think that you are talking about this new tool, gen dwarf k-sims, and I expect that we will switch to it sometime in the future for when it comes to SLES. But I hope that we switch to it in Tumbleweed quite soon, because it's one prerequisite to enable Rust support in the Tumbleweed kernel.
Okay, thank you.
Yeah, we are at the end, so thank you.